Okay, so we are doing ring theory today. Welcome back. I mean, people who are in the meeting already know this. I'm like saying for, I guess, YouTube. It's been a while since I've taken my last lecture. Uh, okay, and I think this will be like part of a series of lectures. Like, I'll take more lectures on ring theory. Not just rings, I'll like get to other parts of algebra, like commutative algebra, build to algebraic geometry, Hilbert-Nadensak. Okay, that's too far ahead planning, but we'll see. We'll see like based on like how people like this class. Anyway, so we'll be discussing rings today, and more specifically, we'll be discussing commutative rings with identity. Well, all rings have identity, and like it's just like easy. Like for sanity, we'll only be working with commutative rings. Oh, I really can't. Will you do Artinian and Noetherian today? So Hilbert-Base's theorem is about Noetherian rings. So I'll give that as a buffer problem to like people who know everything. Allegedly in no piece. 2027 guys, trust me. No, actually no, it's the final problem in boards. Okay, commutative rings identity. Okay. Uh, so what is a ring? Well, a ring is an attempt to generalize, I guess, like the integers to well everything. This easy problem don't come in. Okay. A ring is well a set with two binary operations. Uh, Basically, okay. In general, intuitively, a ring is anything where you can add and you can multiply. What does that mean? Well, it means a ring is a set R along with like two operations, plus and x, and the operations satisfy like a few properties. So for all a b, like just assume like for every single statement I'll write it's for like all a b c and r. So a plus b plus c mm, equal. Actually, wait, can someone like I mean I'll just mention them. It's not one. Introducing rings without groups is just unethical. No one cares about groups. Like it's fake news. I'm telling you. Like group theory is not real. Cool. Aadish, get a pen and tab. Okay, wait. I don't know where it is. I need to like find it. I went back to India and then came back and wait. Actually, wait. I can probably like. Oh, it's right here. You are so right. I'll use them like pen like this pen tab. Actually, I'm like not that good with it. Maybe okay. Where is the pen? Uh, your chat. Like I had. I found my pen. Okay, chat. Can we? Will handwriting improve? I would say no. I don't think this helps. But let's see. Okay. So addition has to like. So the point is, a ring is anything where you can add and multiply, and like the formal definition, we are just saying addition has to behave like addition and multiplication like multiplication. Yeah. So addition is associative. So a plus b plus c is a plus b plus c. A plus b is b plus a, and same with like भाई भाई ठीक है like but the thing no one cares about what groups are like trust me. Okay, like I heard addition as addition. Like, next enigma clue just drop. Yeah, multiplication is associative. uh Multiplication distributes over addition. So a into b plus c equal a into b plus a into c. There exists zero in R. OMC chat has suffered a significant quality drop. Is this because of the Sophie students? Like, I don't need to say this because addition I have already said is commutative. Okay, but whatever. For all A and R, there exists minus A and R that A plus minus A equals zero. Okay, okay, let's and yeah, there exists one. Nah. A and R for non. Yeah. Okay. I'll just writing everything down. Okay. So a ring is anything that is anything where you can add and multiply. But like, what does it mean to be able to add and multiply? So that means that like addition and multiplication behave as you would expect them to behave. So a plus b should be b plus a. A plus b plus c should be a plus b plus c. Same with like multiplication should also like associate. So this is called associativity, and this is called commutativity. So addition should associate and commute. Multiplication should associate. Multiplication should distribute over addition. So a into b plus c should be a into b plus a into c. Uh, and there should be some sense like there should be a zero element, which is such something that a like adding zero to anything doesn't do anything. Like a plus zero is a. There should be a one element, like there should be an additive identity and a multiplicative identity. So a into one should be a. Yeah, we are getting to like multiplication should commute. No, associative is not both. Like associative is just this bracket switching. Yeah. And every single element should have a negative. And the negative is defined as just something such that a plus minus a is zero. Okay. This is what rings actually are. Like rings with identity. But like rings with identity are just rings. No one like considers rings without identity rings. But for our purposes, all rings will be commutative. And commutative means that multiplication also commutes. A into B equal B into A. Okay? So for today's lecture, a ring is just anything that satisfies all of these. And like this is a lot of words, but like the point is you can add and you can multiply, and addition and multiplication behave as you should. Otherwise, it's non-commutative. Yes. Okay, can someone just give me examples of rings? The definitions don't matter that much, just examples should make this clear. Just unmute and shout. Or type in chat.
Z.
Yes, Z. The integers are a ring with normal multiplication and normal addition as their operations.
Rx.
Rx. So R like the set of all polynomials with real coefficients is a ring. Once again with normal addition and multiplication.
And like
Not
you could make
Mod
Rx
C.
where R is any
yeah.
commutative thing.
Yeah, we'll get to
Bro,
that.
mod K, mod K, mod K.
Yeah, real numbers are a ring, rational numbers are a ring. Yeah, mod K.
Integers mod K.
So the first interesting example is Z mod KZ. So this is just integers mod K. So you can say well we'll think about its elements a bit differently in some while, but you can just think of this as the set like 0, 1 all the way to k minus 1 with addition and multiplication defined mod K. Does everyone see like why all of these are rings? Yeah?
Yes.
Yeah.
Yeah.
Great, everyone. Can we have a number ring? What? Yeah, C is a ring. Of course. Wait, why is this like not working? Because there might be a small chance my tablet is like out of battery. So we are going back to bad handwriting soon enough. Oh, what? Even my mouse. Can you repeat mod K? Yeah, I can repeat mod K. Wait. Why is this not working though? Is the question. Okay, I've gotten back to. What about not tab like my writing pad? I don't know. It's stopped working, so I'm back to bad handwriting. Yeah, okay, mod K. So for example, mod 3, Z mod 3Z, it's just the set 0, 1, 2, and you define like addition and multiplication like cyclically, mod 3. So 2 plus 1 is 0. 2 plus 2 is 1. Like 2 plus 2 is 4, and 4 and 1 are congruent mod 3. 2 into 2, you're wrong about M2R because all my rings are commutative today. Yeah. And 2 into 2 is 4, which is 1. Is mod K clear?
Yeah.
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 Okay. This is what the ring is. Everyone's happy. Okay, we will like do more exotic examples later. Okay, we'll get to that.
What did we do till now?
Just defined a ring for this lecture, all rings are like commutative and gave some examples.
Okay.
Yeah. Okay. Now, so the rings are a generalization of Z in some sense, right? So Z, as you would know, is like, okay, what's nice about Z? What's like a common thing we do to solve problems of NT? Oh yeah, just zero is a ring. Maybe I should have mentioned that. But let's see. You can do factorize prime GCD. GCD. Okay, everyone seems to think GCD. Bezoot. Okay. Yeah, all of these are like good things, but they just complex numbers are a ring. Size, induction. Okay. Yes. Rudranch. This is the answer. So, of all the things mentioned, induction doesn't really generalize to arbitrary rings, unfortunately. Bezoos and GCD and primes and factorization. All of them generalize to some rings, which we will do maybe in a later lecture. Modular arithmetic is the thing that generalizes to all rings. And it's, well, that's basically what this lecture will be about. Okay. So, can someone think how modular arithmetic generalizes to arbitrary rings? Like, just guess the definition. Remainders. Okay, what does remainder mean? Because you don't have Euclid's algorithm in every ring. So you don't know what remainders are not really a thing anymore. Define everything cyclically. Okay, let's take a example. Rx, right? Where R is the real numbers. Okay. So what do you mean? Like, suppose I want to mod this out by X, right? Like Z mod 5Z. Like similarly, like suppose I want to like mod Rx out by X. What would that mean? Like you can't just say cyclically because like there is no ordering in Rx, right? Yeah. We did do this in proof of FTA, but like we did it very fast there. So like I'm actually like introducing it like insane means what everything means. Like what is an ideal? Like the point is like you can't say cyclically. Okay, like in Z you have an order, like right, 0, 1, 2, blah blah blah. In like say ZX, you no longer have an order. Like sure, there's just the integers, but then there are linear polynomials.
And
Where do
you
you place
can
those?
induce order, I think. Like if you take the identity element, then consider addition of multiplicative and
Yeah, okay, but like okay,
multiplicative
consider like
identity.
ZX, right? So you can like okay, so you're saying like define 0 less than 1, and then like 1 plus 1 you say is like bigger than 1, right?
Yeah, exactly.
And keep going. But like where do you place X?
Like if it occurs in this, like wherever it occurs in
But
this one plus
like
plus.
this is like the ring of polynomials. Like X is just a polynomial. It doesn't exist anywhere. It's not like 1 plus 1 plus 1 plus 1.
Okay, this doesn't span all elements, right?
Yeah. So the point is trying to use like order or like cyclic stuff to generalize modular arithmetic is sort of not gonna work because that doesn't exist in general rings. Uh, how about this? Okay,
Like
so
in this, we could like to divide in mod x, we could take the like remainder of the polynomial by division of x.
that's a good idea, but what are like arbitrary rings? Just any of these things we did. Z, Rx, RQ, Z mod K, Z, C. Sure. Yeah. Wait, as I was saying. Okay. Let's go back to Z for a bit to gain some more intuition. So when do we say, like, suppose we want to like consider Z mod favorite prime, I don't know, like randomly picked prime. When do we say that A and B are congruent mods? Numbers I won't say.
Yeah.
What does this statement mean?
The
67
numbers you
divides
A
a
won't say
minus
minus
b.
will
B is
divide A minus
divisible
B.
by 67.
Yeah. 67 divides A minus B. Okay. And how can we write? Yeah. Same remainder is something I'm not going to do because, well, same remainder doesn't make sense in general rings. I never realized 6-7. It's in fact a irregular. Is it a regular prime or irregular prime? It's a very special prime. I know that in algebraic number theory. No, it's yeah, it's because it's a Hermite prime. I think that's what they're called from algebraic number theory. Yeah, that's why I picked 6-7. Trust me. Trust me. Okay. 6-7 divides a minus b. How else can you write that?
A minus b is equal to 67 times an integer.
Yeah, k and z. Right.
Yes.
Okay. So you modding out by an element of z, for example, 6-7, is just saying that two elements are equal if their difference is a multiple of that element. Right. Is there anything in this definition that relies on the fact that we are working in z?
Nothing. A is integer.
Yeah, but okay, but like if we replace that by
Nothing.
something here, we replace that by the same thing here, right?
Nothing. Yeah, just the difference. Like just subtract, and if the thing is divisible by that.
Yes. So
How
the
would
way
you
we
do this
define
in,
hmm,
sorry,
So
but
maybe you
how
like
would
take
you,
any two elements.
one by one. Keshav first.
yeah, so here we're saying that A minus B is like 67K, right?
Yeah.
So in some sense, we're using magnitude. So how would you do this in complex numbers?
What do you mean you're using magnitudes? You're just writing it's like there's exist an integer such that a minus b is 67 times k.
Yeah, but then how would you generalize to complex numbers or something?
Okay, there's a reason modular arithmetic and complex numbers is stupid because there will always be a complex number that's like 1 by like 6 like a minus b by 6-7, right?
Yeah,
Yeah, so like you generally don't do modular arithmetic and complex numbers or real numbers or anything that's a field because stuff is stupid. At
I see.
least I'll explain like what that means in a bit. I think like ZX is a better example. That there it will like make more sense. But in general, so everyone can sort of like guess how this definition generalizes. So R mod A, where A is an element of R. Oh god, the chat has like gone to shit. It is my fault. It is entirely my fault. Let's not take like modding out by say Q is we say that two elements are equivalent mod Q if A minus B is equal to
Q times another element of ring, right?
Q times K for K in the ring.
Huh.
Okay, we are most attentive. Okay, so first of all, we still need to go and verify that this makes sense. Like we can do normal modular arithmetic stuff. That means so like if we have two modular equations, we can add them. We need to verify that still makes sense. We need to verify multiplication makes sense. Like everything we know about modular arithmetic generalizes.
I mean, okay, wait. So, if you have like zero is a ring, you said, and you're saying that thing always modular arithmetic generalizes to any ring. So
Hmm.
that means zero is some cube k, right? Like, but k has to be zero because you're having that as
Yeah.
the ring.
Um,
So,
hey,
how
wait,
is like
are you doing modular arithmetic in the ring zero?
yes,
I mean, now the point is any element you mod by, like nothing changes. Everything is already zero. Right? Like
yeah, right.
you, you,
Everything is
you
already
You can't like I mean the only element you can mod by is zero. Like
yeah,
which
yeah. That's
which
not
is
defined, right? Mod by zero is not defined.
I mean no I mean in the zero ring mod by zero is defined. Like the point modding by zero is like doing nothing. So if you put like zero here, what does that mean? We say two elements are same if a minus b is a multiple of zero. That means a is equal to b. So modding out by zero just means we don't do anything. It's the same ring all over again.
Okay.
Right, that makes sense?
Yeah.
Okay. So A minus B is QK. Hmm. Okay. So what am I saying? Okay. Now, can people like just quickly verify these facts? Like just shout out the proofs. So
Do we still use the congruency symbol in rings? Or like,
we generally actually don't, but I'm using it right. Like it's a perfectly valid to use it. No one does it for some reason.
I mean, if x divides a minus b, x divides b minus a.
Why? Like the thing is division. Like try to frame all your proofs like this because we don't know like things we like suspect are true about division are, might no longer be true.
I mean,
But
okay,
like
so a
Division
minus b is
by
equal to qk. So b minus
hmm,
a is q times minus k, and k minus
yes,
q.
yes. Uh, addition of C and multiplication by D.
okay, so the addition by C follows from the fact like you can addition is commutative, so you can basically rearrange to cancel
Is
C.
subtract.
Yeah, and this follows from the fact multiplication is distributive over addition
Yes.
and hence subtraction. Also, I guess maybe I should have mentioned this. Like these ring axioms imply that zero times anything is zero. You can prove that. It's not hard, and there is really nothing gained for like trying to do it. Like I let you prove this. Call this homework. It's not hard. It's like you write zero as like a plus
Zero
minus a
plus.
and then like spam distributivity. No, one plus minus one and spam distributivity or something. Hmm. Doing homework in it's not 2026, guys. It's still 2025. You're lying to me. 2025 did not end. Anyway, so does modular like everyone can see like why like the basic things about modular arithmetic should generalize. We no longer have anything like Fermat's little theorem or Euler's theorem, but the basics generalize, right? Everyone, I assume, can hopefully can see that. Already at 7% zoom. Oh, I keep zooming out or something. We'll fix that. Oh, also that I can no longer see the chat because I accidentally closed it, so I'm free from your brain rot. Oh no, I found it. Never mind. Anyway, now let's do a problem to sort of like explain why this is useful and see that we can like generalize further. Okay, so I'm actually taking a problem from the OMC in Momok or Sophie in Momok 3. So, spoilers.
Of this. You had something with ideas and all this.
Yeah, guys, come on. Okay, before we do this problem, let's actually like let's do one more example of modular arithmetic. Okay. Okay, so consider a ring ZX. Right. Okay. What does modding out by 2 mean in this ring?
Categorizing them like even and odd.
But like we have ZX. So like
Oh,
what will
then
the elements look like? Just
okay, so like coefficients taken mod too.
yeah, basically, right? Like you're this is the same as taking coefficients mod 2 because if like I mean yeah.
Yeah.
Like
Like
two times a polynomial is just like any polynomial whose every coefficient is a
coefficient.
multiple of 2.
Yeah. And like
Right.
difference of two polynomials is a multiple of two if and only if all their coefficients are the same ones.
Exactly. So this is like taking coefficient mods 2. And similarly like mod n. Like it works the same way. The question is, what about modding by x? What is zx mod x? Also, like the notation for modding out is this. Like if you're modding out an element, you write it in brackets and place it like
Basically
this.
just taking the constant part of the like the polynomial.
Okay. Can everyone see why that is? Just z? No, no.
Yeah.
Like basically just taking the
Uh,
polynomial function when
Rudransh,
you put 0. Yeah.
Rudransh, Zx is the set of all polynomials whose coefficients are integers. X is like just a term. It's a variable. Like the elements of these rings are polynomials. X doesn't have a value. Okay. So two elements are congruent if like P minus Q is a multiple of X. That
Yeah.
means P minus Q has no constant term. Hence, P and Q have the same constant term, right?
Yes.
Yes.
So this means that like this ring, like ZX modding out by X, this ring is the same as the like this symbol we use if to say that the rings are the same. I'll define like homomorphisms in a bit, but you can guess what that means.
Wait, isn't this
Yes.
isomorphism?
Yeah, that's isomorphism. Like the point is ZX modding out by X. This means that the only thing we care about is the constant term, right? Two polynomials are same if their constant terms are same. So the fact we are only caring about the constant term, and like that means none of the like actual polynomial part matters. So ZX mod X is just like a fancy way of writing Z. Right. Okay. What about ZX mod X minus 1?
Can you please
Okay,
repeat
that's just P of
ZX?
1.
Wait, Sanskar, wait. Ayush, yeah?
Can you repeat ZX how it is Z?
Yeah, okay.
The
So, no,
congruent.
it's not ZX. ZX mod X. Right.
Yeah.
So, ZX mod X, two elements are same if their difference is a multiple of X. Right? That's what we define modular
Okay.
arithmetic as.
Yeah.
Multiple of X means that like P minus Q, there is no constant term here. Every term has an X in it. Right?
Okay.
That means P and Q have the same constant term.
Yeah.
So saying that two things are congruent mod X is the same as saying they have the same constant term. Right?
Yeah.
So ZX mod X is like a fancy way of saying only look at the constant term, ignore everything else.
But their
Okay.
difference can be multiple of x,
Thank
right?
you.
I mean, the difference will be multiple of X only if their constant terms are same, right?
No,
Yeah.
but if constant term difference is divisible by x.
No, X is not a number. X is just a variable. Like these are polynomials. This is X the polynomial, not like X. X doesn't have any value.
Okay.
Do you understand, Ranch?
Yes.
Okay. Okay, ZX by X minus 1.
The value of the polynomial at 1.
That is correct. And let's give me a second. Like, can someone else tell me like why that is? This ring is also the same as Z. Can someone tell me why?
It is
That
like
is
we are
same
replacing all the x's with ones, and then we still get an integer, and we can get any integer by taking a suitable polynomial.
Yes. Yes. So the point is, in this ring X minus 1, X and 1 are the same. Right? X congruent to 1. So, for any polynomial, like since X is the same as 1, you can replace X by 1. Which is like another way of saying evaluate the polynomial at 1. Right. And the other, like, the normal way of like writing that is like P minus Q is divisible by like is a multiple of X minus 1, like due to factor theorem, if and only if like P minus Q is 0 at 1, which is like saying P of 1 equal Q of 1. Right. So
Yeah.
saying mod X minus 1 is a fancy way of saying that you look at the value of the polynomial at 1 and ignore all the other information about the polynomial. You call two polynomials same if their value at 1 is the same. When you add them, you like just care about their values at 1. Like you're adding their values at 1, you don't care what else happens and stuff like that. Okay? Does that make sense to everyone?
Yeah.
Yeah.
Okay. So like the way we like rigorize this is sort of so a ring homomorphism that like if R and S are rings, then a function from R to S that preserves the operations. So like f of A plus B is f of A plus f of B. And okay, I'm saying it like in a like I should say that this addition is like addition in R and this addition is addition in S. And like f of AB is f of A f of B. And f of 1 is 1. The last one is just needed. It's needed because like to say that we don't have like stupid homomorphisms. Don't worry about that one. Okay. So a ring homomorphism is just a like function between rings that preserves the ring structure. Oh, like f. Does anyone get what a ring homomorphism is?
Can you repeat once again?
Yeah. So, ring homomorphism is like any function between rings that like preserves addition, preserves multiplication, and preserves one. You can prove like the other things that seem like obvious. Like it will preserve zero, it will preserve subtraction, it will preserve like everything else. Like everything you expect it to preserve. This is a ring homomorphism.
Yeah. Okay.
So,
Is it a
uh,
function?
what?
Is it a type of function?
Yeah, it's a function between two rings.
What is S?
R and S are rings. I should have mentioned that.
Okay.
Sorry. Yeah, R and S are rings. Anyway,
Rings
R,
are
R and
defined
S are,
such that they satisfy these conditions, right?
yeah, a ring homomorphism is any function between two rings that satisfies these conditions. Okay.
So okay.
And if it has an inverse, like an inverse homomorphism, or equivalently, if it's a bijection, then we say that it's a isomorphism. That like so what like the rings are another way of saying is that the rings are the same. That you can like transform between the two rings and nothing changes. So wait, for example, actually this problem we'll do like much later. I don't know why I like mentioned it already. Mm, for example, consider a ring Z and the ring Z mod PZ. Right. So like the normal so Z is just all the integers and Z mod PZ is just 0 to P minus 1. Right. And this homomorphism is defined as like f of A is just the remainder of A mod P. Aaron, just turn off the chat.
Just written A mod.
Yeah, remainder of A mod P. What was I supposed to write? Right. So like and like this is what I like this is what you're verifying here, technically, like when we did all of these. That f of A plus C equal f of B plus C, we are verifying that like this is indeed like a homomorphism. That it respects the operations of addition and multiplication. Okay?
Yeah.
Everyone understands? Yeah.
Yeah, yeah.
Anyway, so when like what I'm saying here when I say like zx by x minus 1 is congruent to z, and like more generally, so the thing you can show like for any ring R, Rx mod x minus k is congruent to R by like this function for any polynomial like p of x, f of p of x, you send it to the element p of k. This is how the function is defined. Okay, so what I'm saying here, okay, so above we show that like intuitively zx modding out by zx is just looking at the constant term and nothing else. That means it's like the same as integers. Zx modding out by x minus 1 is just looking at the value at 1. So we don't have any like extra information. We just have the information of one integer. So it's the same as z. And zx by like similarly, zx by x minus k, that will be just taking the value of the polynomial at k. So it's once again just the integers. Right. Everyone, that makes sense to everyone? I guess so.
Yes, yes.
Yeah. So what we like the way we like write this like in the rigor is we say that for any ring R, Rx by x minus k is the same as R. And the reason they are the same is you have this function. For any polynomial in this ring, you map it to like the value of the polynomial at k.
Yeah,
What
that's
is
an
the
isomorphic one.
inverse?
Okay, so the inverse is for any k in R, you map it to the constant polynomial k.
Oh,
And not just that, like the point is you have like modded out by x minus k, right? So for example, the function z to z mod pz, like so if you like want the inverse of 0, 0 comes from like 0p, 2p, or and everything else, right? All multiples of p, right?
wait, but how is the second function you said the inverse of the first one?
Because so okay, so for inverse, what we like this function g, like g of k is just the constant polynomial k, right?
I mean, words won't exist, right? Because like it's not bijective.
No,
Yeah, exactly.
I'm getting there. So I'll get there. Wait, let's see that. Okay. So first of all, okay, f of g is like same, right? Like if you do g, like you send k to the polynomial k, then you do f, then you get k back. So f of g is identity on R. We need to verify g of f is identity, right?
Yeah,
Sure.
yeah.
Yeah. Okay. So g of f. So we have sent. Well, you need to. Yeah. So suppose g of f. Suppose we take a polynomial p, right? So f of p will be like the number p of k, and g of p of k will be once again like now the constant polynomial p of k, right?
Yeah.
So we started with p of x, and now we have p of k, and you're like these are like not the same things, right? How is this identity, right? Right?
Yeah.
Yes.
But the thing is, we are not working in the ring Rx. We are working in the ring Rx mod x minus k.
Okay.
The point is p of x minus p of k. This is 0 at k. So by factor theorem, and you can prove factor theorem works in arbitrary rings. Like the proof is identical. Well, at least like for monic polynomials, you can like prove it. For non-monic, it's stupid. We'll get to that. Anyway, p of x minus p of k is x minus k times something. So p of x and p of k are the same polynomial. At least like because we have quotient like we are not working in the ring Rx, we are working in the ring Rx mod x minus k. So we just like when we are working in Z mod PZ, like Z mod 5Z, we say 2 and 7 are just the same things. They are not different. So P of X and P of K are just the same thing. Does that make sense?
Why do we call it Z mod 5? That is, shouldn't it be like Z mod 5?
Okay, we'll cover the notation when I like define general ideals.
5Z is like what the ideal is written as.
I mean, you can write it as Z mod 5. Like this is valid notation. It's like no sane person uses it.
Then you have the brackets.
Yeah. Then you need the brackets. I'll explain like what this means in general after I cover generalized ideals. We have not gone as general as we can yet. Okay, but is everything clear so far? Also, Shreya, I know I like promised you like Noetherian rings and like the buffer problem, but like I need I need like some free time to do that. Anyway. Okay. If everyone's clear so far, now let's try to do this polynomial. Like, let's try to do this problem. And okay. Wait, how many of you like did this problem like when you gave the mock or like just tried the problem later on? I mean, okay, those who like don't know like the normal solution, try to find that. But what I want you to do is try to find it using modular arithmetic in ZX. And now that we have some free time, maybe I'll like give a buffer problem for Shreya. And you guys will understand the buffer problem later a bit. Okay. Okay. So those of you have not done the problem, try to solve it normally first. And those of you who have, try to write your solution slightly in like the language like I just taught you, like modding out in the ring ZX. Okay, Shreya. Uh, no one like anyone who does not know what ideals are, like this is not for this is a buffer problem. Okay, sure. Let R be like an arbitrary ring. Okay. And all rings are commutative for us. We say that R is Noetherian if for any sequence of ideals, it's like ideal I1, in ideal I2, in ideal I3, and an infinite sequence. This sequence is eventually constant. If every sequence is eventually constant, then we say R is Noetherian. Okay.
Okay.
Prove that R is Noetherian implies Rx is Noetherian. This is Hilbert-Bass's theorem.
Okay. I'll
And I also like this is like very Ollie style problem, by the way. Anyway, we'll get back to that. We'll get back to that.
Isn't this
Anyway,
on the OMC mock?
What?
This is on the OMC mock.
Yeah, this was on that's where I took it from.
Are you going to define Noetherian rings later on?
Probably not in this lecture. Like I have to like define what an ideal is, and I think that then I like try to define what a splitting field is first. Like I can't do everything in one lecture, but I want to take more lectures on ring theory if you guys like this one. Uh, yes, yes, yes. Okay, so Sanskar has the solution. Okay, so here's the thing you do. Okay. So first of all, you consider these polynomials as elements, not in like ZX, but in the ring ZX mod out by x minus 2. Okay. So we know this is the same as just evaluating the polynomial at 2. Right. So the first polynomial becomes 6, and the second polynomial becomes 6. Like 2 square plus 2 is 6, 2 square plus 2 is 6. Not that deep. Anyway. Now, short solution. Yeah, and the point is, Sue, she can like product or difference of any two polynomials. That will still be like add like the point is adding polynomials. Like since this is a ring homomorphism, like zx2 zx minus mod x minus 2, adding here is the same as adding here. So you can just think about working it here. And you can only get multiples of 2, like multiples of 6. By adding 2 multiples of 6 or multiplying 2 multiples of 6, you will only get a multiple of 6. And you can never write x because like x under this map goes to 2. And 2 is not like 2 is not a multiple of 6. Does everyone understand? Okay, motivation.
Yeah.
Motivation is if you look at both of these polynomials, they are same at 2. So that's why you try to.
Or like you can just say that their difference is x minus 2. So
Their difference is x minus 2. So that's why you write 2. Yeah. Anyway, it's like the point is like this is the sort of thing you do in like general like a normal NT question. What do? You what did I say? Like you have an equation, you want to make a bunch of things vanish. so that you get a smaller simpler equation, right? Or like a bunch of things become same. So like you're thinking of which polynomial you mod out by, so these become the same, and that's x minus 2. But here's one thing that we didn't like. The reason I took this problem is that you realize you do like we have done modding out twice. What we did was we took zx, like we have polynomials in zx. First, we mod out by x minus 2. Okay, this is like not how I should write that, but yeah, and we end up with the ring zx. Yeah, this problem will like reappear if someone takes a linear algebra class. Yeah, zx by x mod x minus 2. And this ring is this width. Yeah. You mod out by x minus 2, which is this like say now we have the ring z again. And then you mod out by 6. And then you have the ring z mod 6z. And that's where like the solution is. Right. So you can see we have modded out twice. Right? Like, does everyone understand the solution to the problem?
Yes.
Okay. Is there someone who like wants me to explain it again? No? Okay. So here's what we'll do. This motivates us. Like, can we do everything like this? Just call this one step. So, like from Z, like our idea of modular arithmetic came from like this. P minus Q is X times H, right? But the thing is, we can do something even more general. Okay. And this is like what like quotienting out by general ideals will be. Like we have still done we have done modular arithmetic 2 times, but that's like still doing like okay, how do I say this? Okay. In Z is very special because suppose in Z, first you do like mod 15, you end up at Z mod 15Z, right? Then you do mod like 5, then you'll just get Z mod 5Z, right? You could have done this in one step. You could have just quotiented by 5 directly. First quotienting by 15 is useless. Right?
Yeah.
That's the question. Okay. Yeah. The thing is, ZX is like not that nice. In ZX, if you quotient out twice, it's not necessary that you can like have done it in a single step. Like as we just saw. Like you quotient out by x minus 2, then you quotient out by 6. And there's like no single thing you can do that goes directly from ZX to 6x, Z by 6Z.
Wait, can you explain this once more?
Like, so integers are nice in the sense, like first you mod out by 15, you get Z by 15Z, right? Like integers modulo 15.
Right.
Yeah. Then you mod out by 5 and you get Z mod 5Z. Right, like first taking remainder mod 5, then first taking remainder mod 15. Someone, can you mute? Yeah. Then you mod out by 5 and you get Z mod 5Z. Right.
Oh, okay. So like even if you have the integers mod 15, then you can still do mod 5 and it's still the same.
Yeah, it's like it's just doing it in one step also, right? You can just you don't have to like start by modding out by 15. You could have just modded out by 5 directly.
Okay.
And rings where this happen are called principal ideal domains. Don't worry about it. But the thing is
Where does this fail?
ZX is not a principal ideal domain. In ZX, if you mod out by first x minus 2, you get Z. Then if you mod out by 6, you get Z mod 6Z. And there is no way to go directly from ZX to Z mod 6Z.
Oh, okay.
Right. Okay, so this is the whole point. So how do we generalize modular arithmetic? So I would say the way we do it is we go back to like what we had in integers. So here we had like we want p minus q to be a multiple of x, right? This is how we, or like not p minus q multiple of x, like where did I define general rings? Yeah. We said R mod q is like saying a minus b is a multiple of q. Right. And that was because like we know in modern arithmetic and Z look like this. There's another way to write this. And this is like the notation Mont uses. And it is because that way generalizes better. Yeah, so we like that's the solution. The solution was composing these functions. I am saying that this implies that like modular arithmetic is more general. Like in Z, it never makes sense to like mod out by two different elements because that's just the same as modding out by their GCD. But in ZX, it does make sense, and you get like new things. So I'm like try to like rigorify this idea, like what it makes sense to like mod out by multiple elements. But instead of thinking of it as like a function composition, I'll just like do it in one step. Okay. I hope that makes sense. What I'm trying to do. Anyway, so for those of you who have read Mont, you might remember that Mont writes it in a very different way, like a similar way. X congruent to y mod 5. It doesn't say x minus y is like 5 times k for some integer k. It writes it in this notation. X minus y lies in this set. 0, minus 5, minus 10, and like dots, and 5, 10, dots. Well, okay. I'm like a single step as in there is no single element you can quotient out by. Yeah, it's the same thing. Like saying x congruent to y, like writing x minus y as a multiple of 5. Check your pen pad. The pen pad is like stopped working. Like I'm telling you. I'll figure it out. Oh, it's back to working. Chat. Insane. Yeah. And yeah, this set is called 5z because it's like 5 times the set z. Okay. But so and this is like what the notation is. So x minus y, like x and y are same if they lie in this set. And x minus y, we call this set 5z. And so that's why we like use z congruent to 5z. Okay, how about this? Let's try to like do a new type of modular arithmetic on z. So you have z. I will call x congruent to y if x minus y lies in -1, 0, or 1. Does this work? Does this like define a like normal modular arithmetic? It does. Like
There are issues because then x and x plus 1 will be congruent to each other, but then
yeah, x is congruent to x plus 1.
Yeah.
And now what?
And x plus 1 is congruent to x plus 2, but x is not congruent to x plus 2.
Correct. This is not transitive. Oh, and that reminds me, I should have verified transitivity above. I forgot to do that. But that's also like, you guys can do that. It's not hard. Right. So this is why this set is stupid. Because, like, we are breaking transitivity. This no longer like makes sense. So, let's say we have x minus y in S, right? We define z mod S, where S is a random set, to be this. We call two elements same if their difference is in S. What properties must S satisfy for this thing to make sense? For modding out by S to not be stupid. And like making sense by which I mean that first of all, this is in fact an equivalence relation. That means like congruencies like are like associative, no, sorry, not associative, what I'm saying, reflexive, transitive, blah blah blah. And second, you can do all the nice stuff like adding and multiplying both sides of the equation by the same number. Okay. So can someone say what properties S must satisfy? So here's what we want. Okay, here's what we want. So Z mod 5Z, this notation means we call two elements of Z same if their difference lies in 5Z. Right. So instead of 5Z, let's like do this, generalize this to its logical extreme. Mod out by a random set S. Right. Is not necessarily the multiples of like one element. So here we will call two elements same if their difference
Is an
like
S.
is an S. Yes. So this is now our definition of Z mod S. Okay. But first of all, I'm asking for which S? For which S does this make sense? And for it to make sense, like, okay, what do we want this relation to satisfy? Well, the simplest thing we wanted to satisfy is X and X should be the same. Right. Second, X and Y should imply Y and X are the same. Third, X congruent to Y congruent to Z. This should imply that X congruent to Z.
S should be closed under
So
addition.
basically, S should be like the set of multiples of some element in the ring.
Yeah, but like, okay, let's see. What did you say, Akshar?
S should be closed under addition, right?
Yes. You're completely right. We'll get to that. So you should be able to add both sides. In fact, let's generalize this. X congruent to Y and like A congruent to B implies X plus A congruent to plus minus 2 to the K. Yeah, we'll get to that. Cx congruent to Cy. Do I need to add You can actually show that like these properties also imply that like this kind of multiplication, like xc congruent to yd. This is implied by the previous properties, so that's which is why I'm not writing it. You can like just work with it. You can show that. Like the point, yeah. Anyway, yeah, things are thinking right. Okay, so Sanskar, what you have is like a sufficient condition, but it's not necessary, right? Like so,
Yeah.
currently what we were doing is all our quotienting out so far was like by the set of multiples of one element, by the set of multiples of x minus 2, by the set of multiples of x minus 5 or whatever. Akshat, I'll define what an ideal is. Ashwat, don't worry. That's what I'm like doing right now. Okay. So for Z, the answer is just okay. Let's start with this for Z. Okay. Does everyone understand what you're trying to do right now? We are trying to classify all sets S such that quotienting Z out by S makes sense. And by make sense, I mean this.
So like first of all, like additive identity should be in S.
Yes. So X congruent to X, that means X minus X should be in S. That means 0 should be in S.
And like if an element is there, then its additive inverse should also be there.
Okay, sure. So relation 2 is A and S should imply minus A and S. Okay. What does relation 3 mean?
I wanted to ask, is quotienting commutative?
Yeah. Like since if the original ring is commutative, the quotient ring will be commutative. What?
No. Like if you take a ring, you quotient it with one ideal and then you quotient it with another ideal. But what if you like swap the ideals? The order.
Quotienting is commutative. Quotienting is commutative because like I won't cover this here, but it is the same as quotienting out by the sum of ideals. And ideals commute in their addition.
Okay.
Like I2 plus I1 is I1 plus I2.
And the third implies like S is closed under addition.
Yes. So x minus y is in S, y minus z is in S. So x minus z is their sum. So the sum should be in S. I have not defined an ideal, guys. Like that's just in chat. I have not defined an ideal yet. But okay, so what I'm saying, okay, let's just say what I'm trying to do. So we are trying to classify all sets S such that this makes sense. And every set S for which this makes sense, that's what we will call an ideal. Ideals are anything you can quotient by.
Yeah, so like it should be closed in addition.
A in S, B in S implies A plus B in S. Wait, okay. Let me like I think people are like a bit confused. What's a quotient ring? What's okay? I like said a few words because like someone asked me a question, but I didn't define stuff properly. Let's back up a bit. Okay. So what we are trying to do and what you should focus on is classifying S. Anirudh, Ayush, do you understand that? Like we are trying to classify all sets S such that like Z mod S makes sense. Right. Yeah, you get that. Ayush, do you get that? Hmm. Anyway, all sets S that will work, we will give them a special name. We'll call them ideals. And we'll call the ring Z mod Z by S. Like this is like the ring, like so like the ring of integers mod 5, right? We'll call this the quotient ring of S. Yeah, ideals with respect to Z. Like we will also do this for arbitrary rings. So that will be ideals with respect to that ring.
Uh, isn't the force property like implied by
Yeah.
the third one?
The fourth property, x congruent to y implies x plus c congruent to y plus c.
No. Oh, is that x? Okay, I thought that was cutted. I thought x congruent to y congruent to b implies x plus a is y plus b.
Oh, no, yeah, you're right, you're right. Let's just do this. Huh. Yeah, this is implied because x plus a minus y plus b will be by associativity and commutativity. It will be x
Yes.
minus y plus a minus b.
Yeah.
So by closure under addition, like this is also closure under addition. So we don't need anything new for this. Okay. What about this? What does this mean? X congruent to y, cx congruent to cy.
Like if an element is in S, then like if you multiply any element of the ring to it, it should also
Hmm.
be S.
So, like the point is, this is like saying x minus y in R imply like S implies C times x minus y in S. So, yeah.
What here C is in like R, right? Like C can be anything in R.
Or, well, we are currently doing Z, so in Z, but yeah, C can be anything. Also, I should have, I don't think there's any point for doing this for Z. So, we can do this for general rings. Like, we are just trying to classify what sets we can quotient out by in general rings. These happen to be just the normal sets you work with for Z. Like, 5Z, and like, it's just only in Z. Okay, but let's see. Okay, let's. Yeah, you can. That's because of Bezoots. But let's see what we have done here. It's yeah, yes. Okay, so let's recap what we just did.
Uh, can you
Yeah,
like
you're right.
also tell like over there when we wrote x is congruent to y implies x congruent to c by so c was an LE element in R or c was LE element in S?
Any element in R.
Oh, okay.
But doesn't do anything. Okay. So what we are trying to do, well, I did everything above for Z, but like you can do it everything for a general ring. We are trying to classify the sets S such that this thing makes sense. So this thing means you do define an equivalence relation on the elements of R, where you call two elements the same if their difference is in S.
Yeah.
Right. And the sets that like the sets for which this makes sense will be called ideals. And the ring you get after like doing this modding out, you will call a quotient ring.
Quotient ring like what exactly?
Quotient ring of S, like R quotient S. R
Of
mod S.
S over R.
R over S.
Okay.
Right. Okay. So we were like, so for this to make sense, a bunch of these properties have to hold. And like as Sanskar just did, you can like prove these properties are equivalent to this. So S is an ideal if the following properties hold. First of all, 0 is in S. A in S implies minus A in S. A, B in S imply A plus B in S. A in S, C in R implies CA in R. Oh, and for like, oh, sorry, in S. For those curious about non-commutative, like a left ideal is for anything for which like CA is always in S, and the right ideal is something for which AC is always in S. And the
Wait, isn't like this equivalent to S comma plus comma cross being a group under addition and like closed under multiplication?
no, but the thing is, you're allowing you to multiply by anything in R, not just anything in S. That's the whole thing. That's why
Oh,
it's not
oh,
just.
okay.
Should S be? Oh yeah, S is a subset of R. S is an ideal if well S is a subset of R. 0 in S. Okay.
See, like,
First of all, one
perfect.
of these properties is redundant, which is like not needed. Two. Yeah. Because of fourth property, for n like every multiple of an element should be in S. So uh like A multiplied by -1 should be in S. So you already have that. So this is unnecessary. Is there anything else that's unnecessary?
One.
Why?
Because A into 0 is in S.
Of course, but there's a small issue. Is the empty set an ideal? The empty set does not have 0,
Oh,
so
right.
it's not.
Yeah,
Not
it's
in.
not
But
an ideal.
empty set satisfies 3 and 4.
Ah, interesting.
So 0 in S you can just replace by S is not empty.
Okay, yeah.
That's one of the stupid things. Like
Makes sense. Yeah, makes sense.
this happened to me like in college, bro. Like I'm giving a presentation and like someone asked me to explain what a topology. Not someone like the most famous professor in Imperial asked me to explain what a topology is, and I give the 4 axioms, and he's like, one of these is redundant, and I'm like why? What do you mean? He's like, oh, because the empty union is empty, and I'm like, okay. No one cares about this, but I mentioned this anyway.
Usually, all four are mentioned, right? Like standard.
No, no, the second is actually redundant. Only 1, 3, and 4
Why
are
have you
mentioned.
crossed the second one?
Because the fourth implies the second one.
How?
Pick C equal -1.
Oh, okay. Right. Sorry.
Okay, you have to prove that multiplication by -1 is same as taking additive inverse, which you can do due to
Right.
distributivity. Like, things are true. Like, the things you expect to be true in rings are just true. You can prove them. It's not that hard. I'll leave that as a like, small exercise to fill in the gaps. Okay, so, and we call a set I an ideal if it satisfies these three properties. It contains 0, closed under addition. C should be int. Like C was an integer because like up here, because we were working in Z, but now C is just an arbitrary element of R, whatever ring we are in. Like for example in ZX, we want to be able to multiply both sides by a polynomial. We want to be like AX and BX, we still want to be the same.
So what are all the ideals in ZX? Like,
What are all the good question? Please don't. Okay, no, I'll try to talk about them. And scale, we call it scalar multiplication. We don't call it closure under multiplication because we are allowed to multiply by anything in R, not just anything in S. So these three conditions are what are needed to be able to quotient out by I. Right? This is a generalized. This is as general as modular arithmetic gets. Is that clear? Does everyone understand what I yapped about? Hmm? Okay. I hope people are still following. That's insane. Oh my God, insane. Amazing. Oh, wow. People. How is this? Okay, that's great. Okay, so first of all, let's quickly go back to the problem we just did. And okay, let's actually, no, before we do that, I should like explain what an ideal generated by something is. Okay. So I'll now write some notation. Okay, so first of all, for a ring R, we write GR, where like G is an element of R, to be set of multiples of G. Like GR, R and R.
by ideal generated by like something, do you mean the set GR?
The ideal generated by an element G. I mean the ideal GR.
Yeah, yeah.
Right, GR, and this is also denoted as G. Okay? It's like G in parentheses.
Okay, that's why when you had to write
Yes.
Z by 5, you had
So
to.
Z by 5Z. Yeah, ideal. Yeah, okay. We got that. Z by 5. Uh, ZX by like X minus 2 is the same as, for some reason, like this is just like a standard thing. For everything, like for Z, you use like NZ notation, but everywhere else, you use the parentheses notation. I don't know why. Don't ask me. Okay. That's fine with everyone? Okay, so
If your ring is not commutative, then the
then we differentiate between left and right ideals. Like left ideals are where you can scalar multiply on left side, right ideals are where you can scalar multiply on right side.
okay, okay,
And they're weird, and I don't want to talk about them today.
yeah, yeah.
So, okay, so homework is proof prove that all the ideals in Z are NZ. That there are no other ideals. All ideals are just the ideals of like NZ form. And N could be in particular anything. Like 0Z is an ideal, the zero ideal. And the zero ideal is amazing because quotienting out by the zero ideal is the same as doing nothing. Yeah, I guess that's the reason for the notation. Like writing it like this, you still have to put the parentheses. And then like might as well not write ZX, right? Yeah, zero ideal is very useful, guys. Trust me. No, but like zero ideal is like so cinema. Like I was talking with like Anando like about a thing, and like he's like, no, but doesn't Z have dimension zero? Because every prime I like there's no prime number dividing anything. Okay, I actually this will not make any sense because I've not defined anything. But zero ideal is why Z has dimension one and not dimension zero. It's completely random, and this is why Z is not Artinian. Don't worry about it. Please, nothing I said means anything. We will discuss this later. Okay. Now, classifying all ideals in ZX is, well, a bit difficult. Well, I mean, you can do that. But I'll, wait. I'm trying to think. Is ZX hard? I know like FX is like easy. First, you take name. No. This is like setting up for next lecture. This is setting up for next lecture. Like, I'm like making you. Wait, let's see. I believe. Yeah, I believe it can get like a bit weird, which is why I won't do it. You're talking about I was talking about curl dimension there. Once again, no one worry about that. Okay. So we will get to classifying all ideals in ZX is a bit hard, but I will like try to classify all prime ideals in a bit. We'll get to that. But first, let's this is tech. Yeah, this is tech. This is all no one worry about that. I did a bunch of yap there because people asked me like questions using like the notation, but like up to here I hope everyone understood. Now let's talk a bit about prime numbers. Okay. Z mod 15Z. Why is this ring weird?
Because this ring is not a field.
But okay, Z is also not a field, but that is like not that weird. Is there like something else that like something that goes horribly wrong here?
And ideas.
Like 15 is not a prime.
Like what does that mean in terms of this ring?
Like there exist two elements whose product is like 0.
Yes. 3 into 5 is 0. Well, congruent. Yeah.
But like both of the elements are non-zero.
0, 5 and equal. Yes. Non-zero things are multiplying to 0. This is not never something that happens in Z. This is not something that happens in ZX.
Yeah.
So here's the
IDs.
definition. We call a ring an integral domain if this never happens. If A unequal. Yeah, okay. Ayush, yeah. Just give me a second. Okay. So Z mod 15Z is all things considered like a very weird ring. Because in Z mod 15Z, 3 into 5 is 0, while 3 is not 0 and 5 is not 0. Right. Hmm? Multiplication still works. Oh, multiplication works. Anirudh. Nothing goes wrong with multiplication. It's just multiplication gives you stupid things. Doesn't mean it's wrong. It's just it happens to like be dumb. We do mod 4 all the time. Yeah, it's just not integral. And so the thing is, we like when this happens, I think this is like very weird because like this means like things like factor theorem might fall apart later on. Like, right. We don't want this to happen. So we like integral domains are any rings where the only way you multiply to 0 is by having one of these numbers be 0. Okay. Now, only happens for him. Yeah. In Z, this is like easy. Like in Z, if you quotient out by NZ, then okay, no, there's a cinema thing. Okay. So when is Z by NZ an integral domain?
When n
For
is
which?
prime.
When n is prime. Yes, you are wrong.
Oh, and n is 1.
You're still wrong.
And n is 0.
Yeah.
And n is -1.
Yes.
Oh,
Yes.
right.
I think that's it.
Yeah, that's
Basically,
it.
n
Okay,
is
good.
not composite.
Yes, zero is composite by. Zero is composite.
What?
Okay, no. I don't think no, zero is not composite. Zero is not composite. Ignore me. Fine. Fine. Any number where I told you it was zero. You're right. Okay. Okay, so first thing, these two things like we are gonna like forget about it from the future we'll stop caring because what is n equal 1 and 1? That's 1z, which is the same as z, minus 1z, which is the same as z. Right. So we call like the unit ideal is anything that like contains 1, and hence it's if it contain okay. If 1 is in z, 1 is in an ideal I, then since you can multiply by any random element in the ring, you will get everything like R is in I, right? If 1 is in I, then R is in I. For
Like
any
Z
R.
mod 1Z is just like 0, right?
0, right? Yeah. So we will, from now on, we will only consider ideals that don't contain 1, which is the same as saying we'll only consider proper ideals. Okay. Because any ideal that is non-proper, quotienting out by it just gives you the 0 ring, which is very stupid. No one wants to work with it. Okay?
Yeah.
Yeah.
Okay, so you call a proper ideal, which
Yeah.
like
So
not in
yes.
which I is a proper subset of R.
Yeah. So proper ideal is anything that's like a proper subset. It or equivalently it doesn't contain 1.
Hmm.
Okay. Equivalent to 1, not an I. Okay. Now, so you'll see, okay. So Z by NZ was an integral domain whenever n is prime or n is 0. We ignore like these stupid examples. Okay. So this motivates a definition. We generalize the so by the way, 0 is not a prime number. Let's see. So for a ring R and an ideal I, we say I is prime if R by I is a domain. Is a like I domain just means integral domain. Okay. The name comes from the fact that in Z, and it's proper. I non-proper ideal, like the full ideal isn't. We don't call it prime.
But if
Okay.
that is the case, then like 1, 0, and -1 were vacuously eliminated, so I was technically correct.
I mean, no, but this is like okay. So the thing is, 0 is not a prime number, but the ideal containing only 0, we still call it a prime ideal. Like, this is just like a like there is no like reason for this, I guess. Like this is just how the definitions developed over time, and these like make all the theorems look nice, so you'll stick with them.
Oh.
Like the thing is, you always like it makes sense to eliminate 1 and -1 because otherwise every theorem you'd have to like write a caveat. But it doesn't make sense to eliminate 0 because the 0 ideal like still satisfies all the theorems we will like discover. Okay. Okay. So definition of a prime ideal. It's inspired by the definition in Z. Like we know like when we mod by prime numbers, we have an integral domain. So we just define that to be the general definition of a prime ideal. Okay? R by A is a domain. Everyone gets this definition. Hello, Ringmaster. Hello. Is that Ohm? Has Ohm taken over? 100% Ohm, right? Yeah. Okay. I just wanted to like cover this definition a bit because this will come back up in a bit. Yeah. The reason I want to do this is because classifying all prime ideals in Z is still like a human task, like ZX. I mean, I think you can even do it in Z, but like ZX is like easier. But we'll do it later. Definition of prime ideal is totally same as this. Totally. No, it's not. In Z prime ideals, no. Z mod P Z are no. PZ are the prime ideals. PZ and 0Z. Z mod PZ are the integral domains you get by quotienting out by the prime ideals. Okay. There's one thing. Oh yeah, what else do I want to do? Let's define maximal ideal also a bit. Yeah, I'll just yeah, sure. Okay, before we do maximal ideal, let's actually talk about what happened above. Okay, no, I'm trying to think what's the best way to do the next thing. Okay. Let's do this. So remember above like what we did. So we ZX, we quotiented out by x minus 2. And R by I is a quotient ring. Yes. And then we quotiented out by 6. And then we got Z mod 6Z. Right. So what's the single ideal that takes us from ZX to Z mod 6Z?
Oh. No.
Sorry, could you repeat?
Okay, so I'm like going back to like the above example we did. So like the everything we did was to like say how we can do this in one step, right? So like from like earlier what we did, we like took ZX, we quotiented out by x minus 2, and then we quotiented out by 6. Right. Remember that, Ryanch? Arham? Sorry.
Yeah.
Yeah. Now I'm saying like what ideal should you quotient ZX by to get Z mod 6Z? Now, this will no longer be a I like okay, one second. Definition. Definition. Okay. Ideals of the form GR or like G, we call these principal ideals. Okay. Now these like this ideal won't be principal. So like you have to like find a better way to classify this. It's like yeah, like it's and like when I say like one step, I mean like you have to find something such that like it follows the same thing as this. Like the function needs to be the same.
Wait, in this definition, G is an element of R, right?
G is an element of R. Right? Like we call ideals like these ideals as principal. Well, as assuming like not proper ideals are also not proper ideals are called principal still. Like not any ideal generated like any ideal that's of this form, set of multiples of one element, we call that a principal ideal. Okay, a lot of people are like pointing out 6 comma x 6x. Yeah, but like I have like not defined how to like generate an ideal from its elements, so it's getting a bit Can you give 5 minutes? Okay. Maybe I like did this in like a weird way. Maybe x minus 2x6 is not the best way. Okay, let's actually
What do we
like
need
go
to show?
back. Yeah, let's actually like go back. Let me like say it again because I think I was a bit unclear. Okay. So this whole process was motivated by the fact that like we can quotient out by one ideal then by another. Right.
Yeah.
Okay, so we like I want to like talk about that. So consider zx. Suppose you quotient it out by x, right? You get z. Then you quotient that z out by like 6, and you get just well this, right? So like the way I should write this as z you quotient out by x, then you quotient out by 6, right?
Didn't we quotient with x minus 2?
We quotient, but like that was making it
Wait,
confusing,
so
I
you
think. So
want
like that's
us
why
to
I'm doing
show
it by
that
x this
there
time.
is no one element, like no one
No,
ideal in ZX so that you can quotient
no.
it out by that.
I mean, I also want. I mean, you can show that, but like what I really want you to show is like just tell me what this ideal will look like that we are like quotienting out by in total.
Like just the ideal 6 plus the ideal X.
But I have not defined the sum of ideals yet. Like tell me in like a way that like doesn't use like notation I have not defined. Like just tell me what I is.
Linear
It's like not.
combinations of elements
Okay,
in the two
so
ideals.
Yes. So Aram is right, but let's like cover this.
I is like 0, 1, 2, 3, 4, 5.
Yeah. Okay, so what no. So what we are doing? So from ZX, we are going like. So here's how you like in general find an ideal, right? You see what maps to 0, right? Like suppose if I was in the ideal I, then like this map, like ring to R by I, this would send I like I is congruent to 0, right? Because I minus 0 lies in I. And in fact, all the things that are congruent to 0 are precisely the things that are in I, right?
This is only when I is prime, right?
No. And this is just true in general. Like
Okay.
if you have a map from R to R by I, then the things in I are precisely the things that are congruent to 0.
Yeah.
Ayush. That's what, okay. What I'm saying, if you have a map R to R by I, like, if you're quotienting out by I, the elements of I can also be thought of as the elements that are congruent to 0. Right. Ayush, is that clear? Yeah. Okay. So, when we are looking at this zx, so first you quotient out by x, you get zx by x, which is congruent to z, and then say you quotient out by 6, you get z by 6z. So what you're like, this map is like saying for any polynomial p, you evaluate p of 0 mod 6, right? This is what this map is. So
Yeah.
quotienting out by x we covered earlier. That's like evaluating a polynomial at 0, and then you like did mod 6, right? So this means if we like want to like write this map, if basically if you want to write z mod 6z as just like zx mod some I, then I will be the set of all polynomials satisfying p of 0 congruent to 0 mod 6, right? Right.
Right.
Clear to everyone? If anyone has any doubts, you can
Can
just
you,
ask me.
can you repeat, please?
Yeah. Okay, so what I'm currently trying to do is I'm trying to combine these two steps into one step, like just a single ideal. Okay. So, like the first step is like you take the ideal zx, you quotient out by x. You understand? Like that's like evaluating the polynomial at 0, right?
Yeah, that's okay.
Then you mod out by 6 and you get z by 6z.
Uh,
Right. So I'm trying to say like, what is the ideal such like that does this in like one step? Like, how is this also like zx by quotient sum I?
Okay, so
Right.
yeah, I got it. Yeah.
And because of this lemma we said earlier, like that's precisely the set of elements that like go to zero. So it's all polynomials which are 0 mod 6. Right. At 0. Right. So you can write them as polynomials. This implies that p of x is equal to 6 times k plus x times g for some like integer k and polynomial g, right? Like constant term is a multiple of 6 plus the rest of the terms, right?
Yes.
Okay, but the thing is like you can also write this a bit more generally. You can write this, that means it's 6 times p plus x times g. Like even if k, instead of k you had a general polynomial here, it will still work, right?
Yeah.
P of x is equal to this. Yeah. Oh,
I
oh,
mean,
not
both are
p,
just equivalent, right?
not p. Yeah, both are equivalent. H. Okay. So, what I'm like trying to say is like what this ideal is called. Okay. So, like I think I should have just done this directly. I like try to like give you like a bunch of like motivation, but I think I went in circles a bit there. So, what I'm trying to say is like here's a notation. Okay. So, ideal G was defined as like the ideal like parentheses G parentheses close is defined as GR with R in R. Right. Uh, G comma H is defined as the set of all GR1 plus HR2 for R1 comma R2 in R. And okay.
Okay, so like suppose if we had to like go from like suppose there is a ring R and we divided by two ideals I1 and I1 I2 in order.
Hmm.
So like the quotient ring that we'll get finally after the two the quotient ring two would be the same as would be the same as the quotient ring we would get by quotienting just by G comma H.
Yes. Yes. So okay. So wait, Shreya there? Oh yeah, time. Oh, it's yeah, it has gone like 3 minutes over. So I think I'll like finish now. We didn't actually do the theorem I want to do, which something for next class. But I think it's good what we did. But let's quickly like give you the jargon here. Okay, first of all, every like you can verify this is an ideal quite easily. Like you're saying this is ideal G comma H is like the sum of like all multiples of G plus all multiples of H. And to verify this is an ideal, first of all, addition clearly works and like multiplication clearly works. And pick R1 and R2 to be 0 and you get 0 is there. Right. Also, can everyone see that this will be the smallest ideal that contains both G and H?
What do you mean by small ideal?
Every ideal that contains G and H will contain this ideal as a subset.
Yes,
Right.
yes.
Because if the ideal contains G, it contains all multiples of G.
G.
If it contains H, it contains all multiples of H. And if
And
it
if
contains a multiple of
it
G and a
then
multiple of H, it contains their sum.
yeah.
Right. And in general, like you can define for any set S, you define this to be the smallest ideal containing S. You technically have to justify these always exists.
Smallest ideal containing
S. Containing S as a subset. Yeah, okay, you shall repeat a bit.
okay.
Okay. So what I did so far was, okay, I defined notation. So we remember like brackets G. This was the ideal that's like all multiples of G. So, and like in the ring Z, these are all the ideals. But in general rings, you can have ideals generated by two elements, which will
Okay,
be,
the notations are making sense now.
yeah, GR1 plus thank you. And okay, the reason in Z, like we never have an ideal with two elements is Bezoots. GR1 plus HR2 is the same set as like GCD of G and H times something. That's Bezoots theorem.
So that is why like in integers we don't have
In
any ideas
integers,
except NZ.
yes, in integers, any ideal, like, I mean, Yeah, basically.
Wait, so
Yes.
how
Now,
can you
like,
prove that
do
like
you have like something like bracket G comma H comma Z and you like call them
Yeah. Yeah.
something like,
Like, so in general, like so you can see how this generalizes to n elements. For any finite set of elements, it's just all their linear combinations.
but those
Right.
n elements have to be linearly independent, right?
No. I mean, if they're not linearly independent, then the point is you can also write it as a smaller ideal. Right. Like
Yeah,
in
but that's
in
like redundant.
integers, it's still not clear. Okay, Ahan, I'll get to that. Let's see.
But like that's redundant if we can write some ideal
Like
as a smaller
in
ideal.
integers, ideal like 15 comma 21 is the same as the ideal 3. So you never write it like that. But you can write it. It's perfectly like a valid notation. No
Yeah, I
one
mean
will.
like so like 15 comma 21 would be redundant, like if we could use just one number instead of two.
Yeah. Okay,
wait,
okay, wait.
how do you prove sorry, how do you prove x comma 2 can't be written as the ideal of one element?
X comma 2 can't be written as the ideal of one element. Yep. It's simple. So I mean, it's not simple, but okay. So the way you do it is you argue X is in this ideal,
Yeah.
right? 2 in this is ideal. Suppose this is equal to some G, right?
Right.
Then then like
G divides expands.
G into something is equal to
Yes.
2 and G into something is equal to
Equal to
X.
X. Yes,
But you can
exactly.
prove the only way that happens is if G is 1 or minus 1. Like,
Like what is that proof?
okay. So 2 is G times some polynomial P, right?
Yeah.
Due to degree constraints, G has to be constant.
Oh, right. Okay.
So G is 2, 1, minus 1 or minus 2. And since this divides X, it has to be minus 1 or 1. But for both of them, like for both 1 and minus 1, this will just be like the whole ideal. But x comma 2 is not the whole ideal. In particular, it does not contain 1.
Like for a ring R, can we obtain like a bound on the number, like the number of elements in a bracket? Like for
Yeah, okay.
ring Z, like we have a
You're
bound
getting
of
there. You're
one.
getting there. You're getting to what I'm like trying to like say. Okay, Ahan. I think I like actually give that like I think I'm like running out of time. I don't want to go too much over time. I mean, I don't know if like you get I think I like end like officially end the class, but then I can like answer like some of these doubts. But everything I answer, I'll probably do in like ring theory too also. Okay. Like let me just like quickly end the class after like saying a few more words. So ideal generated by G, ideal generated by GH. Similarly, you can have like ideal generated by S, you call the smallest ideal containing S as a subset. And if S is infinite, so like what you do here is suppose you have an infinite number of elements like A1, A2, dot, and you want the ideal generated by this set, right? Then, wait, Bunny is on. Oh, sorry. Look, it's like getting hot and like my room is get like if I get out, it's like very cold, but my room just keeps getting hot, which is like good, but it's sad for wearing the bunny ears. So this is the set of all once again summation AI's RIs for Ri and R. But the thing is, if this is an infinite set, then like what does an infinite sum mean, right? You don't know that, right?
Right.
So what we say only finite Ri and equals 0. So an
So
ideal generated by an infinite set, we just say is the set of all their finite linear combinations. And this is still an ideal because
yeah.
you can't add two elements which are finite combinations to get an infinite combination. You'll still only get a finite combination. Okay. Yeah. Maybe a bit of yap. Maybe a bit of yap at the end. But what I wanted to say, like the definition I wanted to give here. Um, okay, does everyone understand like what I said here? Like, so ideal generated by one element is this, two elements is this, three elements is all their linear combination, and for like a general set S, and it's also happens to be the ideal that's the smallest ideal containing S. And for a general set S, if S happens to be infinite, then we only ever consider finite linear combinations to like not have to deal with infinite sums. Okay? Yeah. Yeah. I mean, if anyone's like unclear, tell me. But like what I wanted to like, I just wanted to like give you one definition because I mentioned the word earlier and the people were curious. So, okay. In Z, we have this very nice thing that every single ideals are generated by a single element, right? We say this means that Z is a principal ideal domain. Like, well, domain is because Z is a integral domain. And like a principal, like in general, we have it's called the PIR. Any ring where every ideal is generated by a single element is called the principal ideal ring. Right. But as we saw, this doesn't always happen in all rings. For example, in ZX, we have things like x comma 2 and stuff. Right. But what does happen in ZX is sure, like every ideal can be generated by more than one elements. It's still only ever generated by a finite number of elements. Like, I know I like defined how to generate by an infinite set, but even if you take an infinite set, you can like replace it by a finite set and you'll still get your answer. Okay. So a ring is called noetherian if every single ideal is generated by a finite number of elements. Okay. And yeah, so what K Gupta is saying is like, Sanskar is saying is like, can you like put a bound? And that's something like people don't do, but I think you can do it. I have not like seen it done. Like, yeah, like, but a noetherian is more general than having a finite Ors max, by the way. You can think about that. But anyway, so yeah. And the like the original plan for this class, like, and I'll do this in a future class, is like this the most like one of the most famous theorem. Noetherian means every ideal is generated like you can write it as a generated by a finite number of elements.
Wait,
Is
like when you wrote Noetherian earlier, somewhere you did that inclusion,
yeah.
inclusion,
Yeah,
inclusion.
yeah.
Like,
So here's
Like,
here's
is there
here's
something called Ethereum?
Noetherian. So here's homework. Here's homework.
Like if there is no Ethereum, then there should be something
bro,
Ethereum.
that it's Noether. That's a person's
No,
name.
no, Noether, Noether.
Oh,
Noether.
okay, okay.
Noether from Noether's theorem. I mean, Noether's theorem is a thing in physics. It's also a thing in maths. There's a lot of Noether's
Isn't
theorems.
it called Nether?
I think it's called Noether. Like all my professors pronounce it Noether. Anyway. Oh, but like class is over. Like now I'll just like give you like a few homework problems. And I'll post them again in okay, yeah. First of all is this. So oh, I never defined product of rings, but okay, then I'd actually have to give it as a homework problem. Okay, I'll give you the problem of Noetherian rings. So the thing is, wait, let me actually I can just paste this, right? I have your classes. Yeah, and now like in 5 minutes we will, and I can actually paste this from my notes. I don't need to write this, guys. You don't have to bear with my handwriting. I made notes.
Was
I have latex notes for this. Here's homework.
Bro was preparing for this class.
I was actually like studying, guys. Like I like actually like I don't know. I don't use what is Artinian. Artinian we'll get. Okay, Artinian I'll explain here. Okay, so here's like problem one. You can try this.
Wait, do you know what Abel wrote for Inmo 26p6? He wrote
I know.
something.
Everyone knows
Can
it.
you explain?
It's a meme. It's a meme. It's a meme I told him to do.
Like
Oh, you told him.
what did he like? Is that solution correct or
It's not a solution.
If
It's
you
a
had,
complete meme. Don't worry about it.
it's not correct. If you had asked Aadish to leak proposals, you would have known.
I mean Peaceful also asked like what is the
Yeah, yeah. Okay, so here's problem one. You guys can like I'll post this in here, but you can like take screenshots. No, no, Ors max R is not. This is not equivalent. K Gupta.
Okay, so what
What is Osmax R?
Like, he defined it in like chat earlier. Don't worry about it. It's
Sanskar
not a.
notation.
It's Sanskar notation. So what I did earlier. So this is the one we typically use as the definition of Noetherian rings, but it's equivalent to condition 3 and 4. So like proving 2, 3, and 4 are equivalent conditions is the second homework problem, I guess. Okay. And yeah. And I guess I like write problem like okay, problem 3 requires me to define stuff, but I'll just write it.
What does eventually constant mean here?
There exists a case such that after which all ideals are the same.
Oh, okay. All right.
This is the thing you expect it to mean. Are we getting Inmo P6 lower? No Ethereum ring. Yes, yes. And okay, here's problem 3 is probably like okay, problem 1 might be the easiest. But problem 3 is like easy-ish. Some notation. So xj means what you expect it to mean. Oh, I defined xj here. It doesn't matter. I don't need to define anything. Okay. That's ohm. That's certainly ohm. Anyway, product of rings. You can guess what it is, but I'll like explain it. But okay. Wait, let me end the class. I'm like going over time and I shouldn't.
So like Noetherian implies Orsmax are or like Orsmax are finite implies.
Orsmax implies no Ethereum. Orsmax is stronger, much stronger. Aadish living in classic world.
Wait, what is maximal element?
Wait, what? Where is that? Oh, so, element that's not contained in a larger element.
Sorry?
Yeah, these questions will be posted on Discord. Yes.
Like, what did you say?
A maximal element is any element that is not contained in a larger element.
Larger element?
Like, so suppose any set of ideals, like, for example, if you have a set of ideals, like 5, 15, like just in Z, right? 3, then the ideal generated by 15 is contained in the ideal generated by 5. Because all multiples of 15 are multiples of 5.
Isn't Orsmax are being like finite equivalent to the ring
Sanskar,
being
I'll get to you.
larger?
After class ends, I'll talk to you. I know what you're doing wrong. But the thing is, neither the ideal nor 5 nor 3 are contained in a larger ideal. Like, in this set. Right?
So 5
So
is maximal.
we say 5 and 3 are like maximal ideals of this set.
But like 3 is not part of this.
Aren't they
We
considered?
say that.
No, aren't they considered a maximal element of an ideal, or are they maximal ideal?
They are maximal. Like,
Yeah, the element is the ideal.
Oh, okay.
This is a set of ideals. This is a set of
okay,
ideals. We say an ideal is a maximal element of this set if it's not contained inside a larger ideal in this set.
Wait, so I can just define a. Okay, fine. Maybe.
But you have to show everything has a max. Like the set can be infinite. Okay. Anyway.
Now the Orsmax.
Wait, no. Let me wrap up the class and stop recording. So these are homework problems. I'll post them again in the group and I'll like explain what C cross C means. Don't worry about that. I just like any questions and like I know like I yapped a bit too much in the end, but so what you want like what I want to everyone to understand is well, what is a ring? What is an ideal? What does R by I mean? And what does I equal S mean? And what's a prime ideal, I guess.
Yeah.
And does anyone have any questions about like what any of these 5 things are? There's like a lot of yap other than that. Like which you can like safely ignore. I have not finished napkin. Like, are you insane? Are you like has Sem 2 finished napkin? Are you crazy? No. What's the okay? Does anyone have any questions about like these basic 5 things?
Wait, what's bracket S? I forgot.
Ideal generated by S. So the set of all linear combinations of the finite linear combinations of the elements in S.
Oh, okay. So like okay that if the S is like a singleton set, then it is a principal ideal.
Yes. So does everyone understand most of what I yabbed? Any questions? Like if you want to ask any questions that are like a bit beyond the scope of the class, stay after like the recording is stopped. I know like Sanskar already has something like ready. Where you add ideals and do quotients of quotients. Okay, yeah, that's fair. That is fair. I didn't like I think I'll also like put that as a homework problem and maybe explain its solution in the next class about like what happened there.
Okay, so
Uh,
Odd's max
wait,
of the ring is just like every ideal would be
but
written as a.
wait. Ahan, I'll elaborate on that after the recording ends because I think it's like a bit like I went a little bit like crazy near the end of the class, but I will elaborate on that. It's a bit beyond the scope, so it doesn't matter that much, so it's fine. But anyway, any other questions? Okay, if there are none, then I think Arnav, you can stop the recording.
Like next class, what are we doing?